Hi class, this is the second video of our new energy unit, topic C2, kinetic energy and gravitational potential energy. So last video we talked about different types of energy, and now we're going to look specifically at kinetic and gravitational potential energy in a bit more detail. So our learning goals are to learn the following terms: mechanical energy, kinetic energy, potential energy, and gravitational potential energy. And we're hoping to learn to calculate kinetic and gravitational potential energies and explain examples of energy transformations. Recall that energy is the ability to do work, and we calculated work, finding that it's sometimes positive, sometimes negative. And if work is equal to the change in energy, that positive or negative work happens when we add or remove energy from the system. Recall that in the types of energy, we can have energy related to motion, kinetic energy, or energy that's stored, potential energy, and then we have different types of these different specific types of kinetic or potential energies. So kinetic energy is energy possessed by moving objects. Take a moment to think, what would have a lot of energy if it was a moving object? How could you increase the amount of kinetic energy? If an object is moving really fast, so the faster an object goes, the more kinetic energy it possesses. If an object is really massive, so the more massive an object has, the more kinetic energy it possesses. So we can calculate the energy associated with the object, in motion by doing 1/2 mv squared. M is mass in kilograms, V is speed, not velocity, but speed in meters per second, and we square that value. And then we calculate kinetic energy, or EK, in SI units, joules. And we can also calculate the change in kinetic energy, but notice that because V is squared, we do need to know the final and initial velocities. It's not good enough to just know the difference in the velocities. And that you can prove that for yourself if you, in the margin, factor out 1/2 m. Vf squared minus Vi squared is not equal to Vf minus Vi squared. So I want you to prove to yourself, do your FOIL method to show to yourself that it's not true. So you really do need to write it out like this. We can't just put a delta here and put a delta in front of the V. We need to know that, like, for example, an object accelerates from 3 meters per second to 4 meters per second. We need to sub in 4 squared and 3 squared. The difference of 4 squared minus 3 squared is 5. Is 7. But 4 minus 3 is 1. 1 squared is 1. So we wouldn't get the same answer. Vf squared minus Vi squared is not the same as Vf minus Vi all squared. Other than that, we calculate this very similarly to just EK. So delta EK is something that we're going to be calculating often. Notice if your final speed is bigger than your initial speed, so you're accelerating, then we're going to get a positive delta EK. So if we speed up, we gain kinetic energy. And if we slow down, our Vf will be smaller than Vi, so our delta will be negative. So we lose kinetic energy if we slow down, and that makes sense. It turns out that work, or that change in kinetic energy, is equal to total work. So this is something we calculate quite often, so it's really important to know this. This principle is called the work energy principle, and it states that the net amount of mechanical work done on an object equals the object's change in kinetic energy. It's worth noting that this is a net amount. So this is based on the net force times displacement. We can sub in for delta EK, 1/2 mVf squared minus 1/2 mVi squared, or we could factor out the 1/2, or we could factor out the m. Let's look at how that work energy principle is derived. So we start from the work equation. for simple case one where force and displacement, or the net force, is the same direction as the displacement, so we don't need the cos theta. We're going to substitute in, if that is total work, then our F is the F net of Newton's second law, F net equals ma. So we're going to get ready to sub in F net equals ma for F. And then for delta D, go back to our kinematic equations that relates to initial and final velocity. And if we're just moving in, if we're just moving to the right and we're just looking at speeding up or slowing down, so not changing direction in one dimension, we can just think of them as speeds. The velocity, the speeds are just the magnitudes of the velocities. So we substitute in equation 2 isolated for delta D and Newton's second law into this. We expand the m and bring the 1/2 outside, and you can see how it's 1/2 mvx squared minus 1/2 mvx squared. The delta, just like the other deltas in this course, it's final minus initial, and we see final energy minus initial energy gives us the work energy principle. So let's try an example. A 5,000 kilogram truck moves along at 15 meters per second. What is its kinetic energy? So our givens are mass and speed, and we can substitute right into EK equals 1/2 mv squared to get our answer of 562,500 joules. Now, if we go back to look at a sig figs, this 5,000 is only one significant figure, so we're going to round this to 600,000 joules. We also mentioned in the previous video that 1 joule is not very much, so very often we use the kilo prefix, or we could use the mega or the giga. Either answer is perfect. So you're not required to convert to kilojoules unless it's stated in the question. Let's try another example. So we have a 60-gram toy that has 18.8 joules of kinetic energy. What is its speed? So now what we're given is mass and energy, and we have to isolate V before we substitute in our numbers. Make sure you practice this isolation step because it happens quite often, and we're heading into the next lesson where you have more than just isolating V from this equation. So make sure you remember the square root. Okay, another example, we have a 50 Newton force applied to an object with a mass of 2 kilograms for a distance of 2 meters. If it is initially at rest, what is its change in kinetic energy? So always take a moment to stop, draw a diagram, write out your givens, check what you're being asked for, and see if there is an equation that connects the given information with the required information. We have force, mass, displacement, and speed initially because it says the object starts at rest. So how do we get the change in kinetic energy? Well, change in kinetic energy is this equation here in green. We don't have VF, so we won't be able to use that at this moment unless we used, unless we were able to use a kinematic equation. Now we have D and VI, but you need 3 things in the kinematic equations to solve for a fourth. We do have mass and force, so we could calculate acceleration through that, and then we'd have 3 knowns, and you could calculate VF and then sub it in here. But actually, the fastest way would be use the work energy principle. And we know force and displacement, the product of those two give us work, and work is the change in energy or the change in kinetic energy. And there's a big assumption here that that force that's mentioned is the net force. There's no mention of any other forces, so I guess we're going to say assume friction is negligible and this is the net force. So our change in energy is 100 joules. That would get on our calculator. Looking back to the question, you have 2 significant figures, so you need to report your answer as 1.0 times 10 to the 2 joules. Often I get the question, is it necessary to report with scientific notation? There's many times where it's optional, but in this case, between standard form and scientific notation, only scientific notation is showing two significant figures. So the perfect answer would have to be in scientific notation and no other answer. Okay, so that was kinetic energy. Let's talk about the other specific type of energy of this lesson, gravitational potential energy. And the reason why we want to learn about gravitational potential energy is it will become more clear in the next lesson when we do conservation of energy, but we need to know what mechanical energy is. That was one of the learning goals of this lesson. Mechanical energy is the sum of kinetic energy, EK, and gravitational potential energy, EG. So we've already learned about how to calculate EK. Now let's learn about calculating EG. And remember that EG is a form of stored energy. So gravitational potential energy is the energy associated with an object due to its vertical position with respect to some reference point. Usually we use the ground as a reference point. So think about what affects that type of energy. How do you have more gravitational potential energy? Well, if the object is higher, then you have more energy. If the object is more massive, then you have more energy. So we have an equation for calculating gravitational potential energy, e.g., equals mgh. M is mass in kilograms. G is the acceleration due to gravity. That is also the gravitational field strength near Earth's surface. We're going to be using 9.81 meters per second squared. Unlike in the textbook, they're using 9.8, so we're using 9.81 in all of your future assessments or lesson examples. So just to follow along, make sure you use 9.81. And times h, which is the height above the reference level, which is usually the ground. That gives you Eg, which is our energy in joules. So when we're calculating gravitational potential energy, or any type of potential energy for that matter, it's really important that there is a reference level that you're always comparing to. So the reference level, we kind of would usually use the ground. So if you are above the ground, or like you would use, I guess, you would choose this level. And if you are above that level, then you have positive Eg. And if you are below that level, you have negative Eg. So you could say, like usual, that the reference level is the ground, and you could dig a ditch, and if you were 2 meters below the ground level, you would have negative Eg. It's going to be strategic to sometimes choose your reference level to not be the ground, and I'll show you in an example. Just like we learned EK and then the change in EK, we're also learning about the change in EG. For EG, we know that delta is final minus initial, and writing it like this, you can actually see, you can substitute in the change of height to get the change in EG. This is unlike for the change in EK, where knowing the difference in speeds is not good enough, and the reason is because it's squared. But here, all we have to know is that the ball has been raised up 2 meters higher than it started. It doesn't really matter that it was 12 meters minus 10 meters. So this equation is mathematically simpler, but we do have the tricky, well, just something to remember is setting your reference. And if you don't do that, you can mess up these problems. Just a word of note that this is only valid when we're near Earth's surface. And also a note that G is 9.81 in units of meters per second squared, or in newtons per kilogram. So those are two different, I guess, they were the same value, but two different units. You can use either of those in this unit, whichever you prefer. So H is the vertical position above the reference. Make sure you pick your reference. With the delta H, for calculating Eg, we don't it does not depend on the path to get to H final. We only care about the final height and the initial height. It doesn't matter how you get there. So you might have gone up 10 meters and down 8 meters and then up 2 more meters. So at the end of the day, you're 4 meters higher than you started. And it doesn't matter, any backtracking, it doesn't matter. Assume H is small enough that G is constant. We had a whole section last unit about how G does vary with varying altitudes. But for our problems, H is going to be small enough that we will just say that G is 9.81. Define your reference point on your diagram. So you're going to be given marks for convention in this unit, and one of those conventions is indicating your reference point on your diagram. So our last example is a 1 kilogram coconut is perched on top of the roof of a 4-meter tall house, which is on a cliff 30 meters high. What is the gravitational potential energy relative to the top of the cliff? What is the gravitational potential energy relative to the water? So we're going to go through this example. We're going to draw a diagram because that's really important. We're going to set a reference level. That's really important. But one takeaway from this example, I hope that you get, is that when you are calculating EG, you need to state what it's relative to. But if you wanted a change in EG, then you don't need to state what it's relative to because it's a change. So, there's also a part C, which we'll get to. So for part A and B, this diagram will serve the purpose of solving A and B. So we want to know relative to the top of the cliff or relative to the water. So we're going to look at this cliff having a dotted line for H equals 0 for part A. Eventually, we'll get to a dotted line for the bottom of the cliff for H equals 0 for part B. So for part A, H is positive 4 meters because we are 4 meters above our selected reference. We have mass and G, and we just substitute in the numbers to get 39 joules. So we would conclude, therefore, the potential energy relative to the top of the cliff is 39 joules. We need to say this part because a potential energy is always relative to something. So you need to state what it's relative to. For part B, we're relative to the water. How is the solution going to change? The only thing that changes is that we sub in 34, positive 34 meters, because now we're 34 meters above our new reference, which is at the water. So 330 joules relative to the water. So you can compare with A and B. You were asked the same thing, but relative to a different spot. So it's really important that you say relative to the water versus relative to the top of the cliff. Part C, which might be cut off in your student example, but I do recommend you write this out because it's a good example to have. Calculate the change in gravitational potential energy if the coconut falls into the water. Change is final minus initial. So it's MGH final minus MGH initial. Since, so because you can choose your own reference, and so far we've chosen 2 different references in A and B, you have to pick one. So there's no wrong answer, but a smart answer would be any reference that allows one of the terms to cancel out. I usually select my final position to be H equals 0, and that guarantees that one of them cancels out. So I substitute in the other term and I get negative 330 joules relative to the water. So my change in gravitational potential energy is negative. That means I've decreased in my potential energy, which makes sense because I'm lower down than I was before. So since I'm closer to the Earth, there is less potential. So now it's time for you to do some practice questions. Make sure that you remember to take a photo and submit your answers to those practice questions on Google Classroom. And remember to complete your exit ticket for this lesson. Have a great day. Stay safe.